Welcome to the second video for electricity. In this video, we have three topics that we're going to cover. We're going to first talk about the anatomy of a battery and how it works. We're going to talk about voltage, and then we're going to do an introduction to current. Now, if you remember from the last video, we talked about one of the requirements for current electricity to happen is to have a charge pump. And most of the time, our charge pump is going to be a battery. So, in order to understand how current electricity works, we first need to understand how batteries work. Now, on the picture you see here is a picture of a sample alkaline battery. An alkaline battery is just a simple battery that you would find in a grocery store, whether it's AAA, AA, C, or D. That is an alkaline battery. Now, before we begin, it's important to note that every battery and its specifics are going to be different. However, the main idea and the main way they work is going to be similar between all of them. Okay, so first of all, let's notice the two ends of a battery. There's the one end of the battery that has the button, or the protrusion. This is going to be known as the positive terminal. The positive terminal of a battery is also known as the cathode. The other end of the battery, which is flush, is going to be the negative end, or known as the anode. Now, for this video, we're going to be talking specifically about alkaline batteries, which are different from lithium batteries, which are usually your rechargeable batteries, whether it's in your computer or your cell phone. So make sure you understand that it's going to be slightly different, however, the concept is still the same. All right, now, inside the battery, you have what's called a carbon rod. And this carbon rod is right here in the center of the battery. Surrounding the carbon rod is some sort of mixture. In this case, it's a manganese dioxide mixture. You don't really need to know that it's manganese dioxide. That's more chemistry than it is physics. But what you do need to know is that inside, when this battery is connected to a wire, this creates a chemical reaction. All right, now when the chemical reaction is taking place, what's happening is it is stripping a bunch of electrons, and those electrons are actually piling up on the bottom of the battery. This is why the bottom is known as the negative, because that's where all the electrons congregate. Now remember, negative charges or like charges repel. They don't want to be near each other. So do you think that the electrons are going to be low in energy or high in energy when they're all smushed towards the bottom? The answer is high in energy. They don't like to be near each other. They're trying to get away from them and ultimately get to the positive side of the battery. However, the electrons are not allowed to get to the positive side of the battery. And the reason for that is because every battery comes with what's called a separator. The separator is separating the cathode from the anode. Or in other words, it's separating the negative part of the battery from the positive part of the battery. So the electrons are stuck. They cannot get to the positive side because they can't get through the separator. However, electrons are very smart, and so they will find any way that they can in order to get to the positive side. When you hook a battery up to some sort of circuit, that is the pathway in which electrons can now take. Electrons will escape out the bottom, move through the wire, because the wire is a conductor, and go all the way around and try to get to the positive side that way. That is how electrons move throughout a circuit. Now, as electrons are traveling towards the positive side, they naturally have to go through circuit loads. In this example, the load happens to be a light bulb. So as the electrons are moving through the wire up into the light bulb and back down, that is where it is powering the device. And in this case, the device is the light bulb. So the electrons move throughout the light bulb, and it goes through, and it continues its journey onward towards the positive side. When the chemical reaction is all done inside the battery, in other words, there's no other materials in there to create a chemical reaction, the battery is depleted, and therefore it is dead. So that's the basic idea. If you were to get a couple things from this video, or from this picture, that would be that electrons want to be low in energy. However, inside the battery makes the electrons high in energy. Battery makes electrons high in energy. Because they're high in energy, they want to get back to being low energy. However, the separator obviously separates positive from negative. And therefore, the electrons have to go through the circuit in order to get to their positive side. That is the basic premise behind how batteries work. Now, in the last video, we started to talk about electrical potential difference and try to explain that. There's another term that we use for electrical potential, and that's known as voltage. So when you hear that something has a certain voltage, it's essentially describing what the electric potential difference is. For example, if you look on the side of any alkaline battery, it's going to read the voltage of that battery, and every alkaline battery is 1.5 volts. What does that mean? Well, voltage or electric potential difference is just telling you the change or difference in potential energy from one point to another. So it's saying as electrons go from one side of the battery to the other side of the battery, their change in potential energy is 1.5 joules for every 1 coulomb of charge. And that's what's down here. Remember in the last video, we defined the potential difference as change in potential energy over Q. Well, potential energy as the units of joules and Q as the units of coulombs. And so these right here are the units for voltage or potential difference. So if the battery reads 1.5 volts, that's the same thing as saying there is 1.5 joules of energy lost for every 1 coulomb of charge that passes through. Now, this is also known as the electromotive force as well. This is a term that's been around for a long time that was used to describe what was happening inside a current. Now, what actually is voltage? We know the synonyms, we know the general idea, but what is it? It's really good to think about voltage as electric pressure. Now, to understand that, let's look at an analogy that we might understand a little bit better. Think about a water tank such as this. You have a big tank filled with water, and then you have a spigot on the side that allows a tap in order for a stream of water to pass through. If this water tank were extremely high and filled with water, the gravity acting on the water would push the water down a lot. And if the water is pushed down a lot, when you open this tap right here, the stream of water that passes through is going to be extremely great. And that's where you get a high amount of water pressure. However, if our water level is very low, maybe down here, then gravity is not going to be acting on that water as much because there's less water, there's less mass. And therefore, if there's less gravity acting on it, there's less water pressure. And if there's less water pressure, the water stream that will be coming out here would be less. And so the same way that water pressure and water level is going to dictate what our stream is through our tap, electric pressure or voltage is going to dictate how much charge is being pumped or pushed through the circuit. Another example is like water slides at a water park. Okay, if you've ever thought about how does the water get from here to up here? Well, there's a water pump, and it pumps the water up here. Remember, that's very unnatural. The water pump is doing something to the water that the water does not want to do. The water wants to come down, not go up. So the water pump puts energy into the water, and when the water gets up here, it has potential energy. It then goes down through the slides, down here to where it is naturally, and repeats the process all over again. If the pump is very strong, a lot of water is going to be brought up here, in which case the water will flow through the slides very rapidly, creating a bigger amount of water and therefore a funner water slide. However, if the water pump is very weak, not a lot of water will be brought up here, and so your water slide will be very lame. So when we think about voltage, it's good to think about it as the same as electric pressure. Okay, while we're on the topic of batteries and voltage, this slide right here shows a few different things when it comes to symbols and some other definitions. If you look at the image on the left here, this is just an animation of what we described before with the battery. Notice the positive terminals at the top, negative terminals at the bottom, and that's because as the reaction's happening, electrons are being stripped and all gathering down here towards the bottom. The electrons then go through the wire around and come back up here to where they can go through the positive end. Now, the mechanism inside the battery that makes all that happen is known as the internal circuit. So the internal circuit is what is described inside the battery, which is supplying the energy to the charge. However, the external circuit is what's referred to as the wires and the loads that the battery is connected to. This is the electrical energy the electric energy is lost by the charge as it does work on the circuit elements. So the battery gives the charges energy. The charges carry that energy through the wires. As the charges get to the circuit load, they drop the energy off in order to power it, and they return to the battery with the energy gone, because now they're in their lower energy state. Notice the symbols for a light bulb. There are two. The first one looks like this. It's like a loop inside a circle. The second one looks like this. Looks like an X inside a circle. Both are appropriate, and you will see both when it comes to drawing schematic views of a light bulb. Now, a battery looks like this with a symbol. You'll notice that one side is longer than the other side. The longer side always is for the positive, and the shorter side is always to the negative. Now you can see that there's multiple lines here. Each set of two lines represents one cell of a battery. Do you remember how I told you that a battery is 1.5 volts? Well, if you ever go to the store and see 4.5 volt batteries or 9 volt batteries, really what that is that's a bunch of battery cells combined into one. So for example, a 4.5 volt battery is really just the same as three 1.5 volt batteries that are connected to each other. A 9 volt battery is really just six 1.5 volt batteries that are connected to each other. And so how we show that is each set of two lines is going to represent a cell. And so in this particular battery, this battery is showing two cells. I know it's two cells because each set of long and short lines represents a cell. So there's the first one, and there's the second one. You draw as many cells as the battery has, but the general symbol for a battery is a long line followed by a short line. And then finally right here, this shows once again how the arrows are moving to show the direction of the electrons moving through. Now, if I wanted to measure what is the potential difference, say from here to here, we can use what's called a voltmeter. This is actually what a voltmeter looks like in person, but this is the schematic symbol for it. How I would show that connected is I would show it just like this. A voltmeter would straddle the two ends of the points we're looking at, and it would measure what is the change in potential energy from here to here as the charges move through. All right, now let's look at one other thing that's going to give us another formula that will be useful. If you remember from the previous video, we learned that potential energy is really just the same thing as work, because it takes work to move the charge or move the ball, whatever it is, into a certain unnatural position. And work is the same thing as force times a displacement. Now, from electrostatics, we learned that force is equal to an electric field times a charge placed in that electric field. And so I can replace F with EQ to get this. So therefore, the change in potential energy is just equal to Q times electric field times displacement. If I rearrange this equation and divide both sides by Q, I end up getting this. And remember, change in potential energy per charge is the same thing as voltage. So voltage is equal to the electric field times the displacement in that electric field. Reminder, delta V is potential difference between 2 points, and it has the units of volts, which is the same thing as joules per coulomb. Okay, so let's do some math problems. We've done a lot of conceptual stuff. Let's do some math. If a light bulb operates on 110 volts, how much energy does it convert from electrical to others when 150 coulombs of charge pass through it? All right, so my change in potential is 110 volts, and my charge, Q, is 150 coulombs. I want to figure out how much energy is being converted. So in other words, I want to know what is my change in potential energy. So I'm going to use the equation delta PE is equal to Q times delta V. Well, my charge is 150 coulombs. My voltage is 110 volts, which remember 100 volts is the same thing as joules per coulomb. So I'm going to write it as joules per coulomb. So you can see that when we multiply them, the coulombs cancel out. And so my change in potential energy as it gets transferred from one form to another is going to be 150 times 110, which is going to give us the value of 16,500. And since the coulombs canceled out, that's going to be in joules. So as the light bulb uses that amount of coulombs, that's the amount of energy that's transformed. Let's look at one more. A charge moves 2.5 centimeters in a uniform electric field of 550 Newton per coulombs. What is the electric potential difference when the charge moves this distance? So it tells me that the charge moves 2.5 centimeters. So the delta X is 2.5 centimeters. The electric field is uniform, and it tells me that that value is 550 newtons per coulomb. I want to know what is the electric potential difference, or in other words, what is delta V? Okay, so in this case, we're going to use the formula that we figured out last, and that's delta V is equal to E times delta X. My electric field is 550 newtons per coulomb, and my delta X is 2.5 centimeters, but it needs to be in meters. So to change centimeters to meters, I move the decimal place 2 places to the left, so that gives me 0.025 meters. When I multiply those together, 550 times 0.025, the number that I get is 13.75. And notice the units, Newton times meter over coulomb. So Newton times meter over coulomb. And do you remember what a Newton times a meter is? That's the same thing as a joule. So I get joules per coulomb, and joules per coulomb is the same thing as volts. So my answer is 13.75 volts, or in other words, 13.75 joules of energy per coulomb is the change as that charge moves. Last thing we want to cover in this video, I know it's getting kind of long, but we'll be done here in just a moment, is current and amps. So we talked about voltage, and the second component of electricity is current, which has the variable I. And current is defined as the rate at which charge travels through a circuit. This is measured in what's known as amperes, or for short, amps. The unit for current is a capital A, and capital A, or amps, is the same thing as coulombs per second. Just how the same thing as a volt is joules per coulomb. And so amps is measuring how much charge passes for every 1 second. Now, let's talk about the direction of current. Conventional current, or just current in general, is always defined as the flow of a positive charge. And that's because when we first started learning about electricity, we didn't even know the electron existed. And so, when we looked at a battery that was hooked up to a wire, we thought it was positive charges that were moving. And so we thought it was remember, this is the positive terminal, this is the negative terminal. So we thought it was positive particles moving throughout the circuit. So this would be the direction of current. Remember, current is always defined as the flow of positive charge. But remember, now we know that it's not actually positive charges that are moving, it's electrons that are moving. So the flow of the electrons is always opposite of the direction of the current. Electrons flow from negative to positive, but current is always defined as positive to negative. I know that's weird, but just remember that it's always opposite of electron flow. Current always is positive to negative. Now, what if we wanted to measure the amps? We use an instrument called an ammeter. An ammeter looks like this, but it has the schematic symbol of an A. Now, the voltmeter, if you remember, the voltmeter had to straddle 2 points. And that's because a voltmeter is designed to measure the difference between 2 points. An ammeter, on the other hand, just wants to see what's the current passing through a point. So an ammeter does not need to straddle a wire. An ammeter can actually just be placed right in the circuit as the electrical current passes through. So let's practice this and end the video. This is asking us to draw a schematic view of a light bulb connected to 3 1.5 volt celled batteries. Be sure to draw in an ammeter and a voltmeter correctly in order to measure the current and voltage drop across the light bulb. Okay, so the first thing I want to do is I want to draw my battery. Notice that it said it's 3 1.5 volt celled batteries. So what I'm going to do is I'm going to draw 3 cells. There's 1, there's 2, and there's 3. And then I connect by wires. This side right here is the positive side. This right here is the negative side. And now we need to connect in my light bulb. Okay, so I'm going to draw a wire up. I'm going to go across here, and I'm going to put my light bulb right here. Does it have to go right here? No, it could have gone right here. Doesn't matter. But this is where I'm going to put my light bulb. And I'm going to have my light bulb be the loop. Remember, it could also be an X, but I'm going to have the loop because that's more commonly used. Now, it says I need to draw in an ammeter to measure the current. So I can do that anywhere. I'll do it over here on the side. So I'm going to put it right here. But remember, it doesn't matter. I could have put it here. I could put it here. Here, the current's going to be the same. If there's particles that go into the light bulb, they have to come out. So it's going to be the same no matter where. And so now I have drawn a schematic view of the battery, of the light bulb, and the ammeter. The last thing I need to do is I need to draw in a voltmeter to measure the voltage drop across the light bulb, because the energy that's going into the light bulb is not going to be the same energy that goes out because the light bulb has now used some. So I need to draw in a voltmeter that is straddling before and after the light bulb. And so I'm going to do it like this. Whoop. There we go. Finally, it doesn't ask us to do this, but let's do it just for practice. Draw in the direction of the current. Would the current go clockwise or would it go counterclockwise? Remember, current always goes from the positive to the negative. This is the positive side of the battery. This is the negative. And so the current is going to go in a clockwise order. Just like that. But remember, in reality, it's actually the electrons that are moving counterclockwise. Okay, let's do a quick check for understanding. The quantity electrical potential is defined as the amount of A, electric potential energy, B, force acting upon a charge, C, potential energy per charge, or D, force per charge. Remember, electric potential is the potential energy per charge, and so the answer would be C. Okay, last one. When work is done on a positive test charge by an external force to move it from one location to another, potential energy increases or decreases, and electric potential increases or decreases. Okay, the key word here is work is being done. So in other words, we're making this positive charge do something unnatural. So we are doing work on the charge. It's gaining energy. And therefore, the potential energy would increase. If the potential energy increases, we will see that the electric potential will also increase, since there is a direct relationship between potential energy and electric potential. So the answer there would be A. This concludes the video on batteries, voltage, and current.